everybody, this is Iftikhar Ahmed back with my new video on interference. Today we'll be talking about Newton's ring in transmitted light ray. In the previous class, we have seen how we will get the beautiful Newton's ring pattern, the circular pattern, and what is the reason behind getting the circular fringes, and we have found out at what particular thickness we will get the condition for dark spot, a dark fringe, and at what particular thickness we will get the bright fringe. And we have calculated the relation between the diameter and order of fringe. Now in this class we will study about the transmitted light ray. The transmitted light ray will also produce a beautiful analogous pattern as that of the reflected light ray, but the condition will be completely flipped. The condition will be completely changed, the reverse condition. Whatever you will get bright at the reflected interference Newton's ring, at that particular position you will be getting dark in the transmitted light ray. If you get a bright fringe at that particular thickness, you will be getting a dark fringe in the reflected light ray. So these conditions will be exactly opposite of the reflected Newton's ring. So let's get started. So actually, before going to start the reflected light ray, I want to tell you a small thing. You should know that most of the students, without knowing this thing, they'll directly jump into the transmitted light ray part and they'll be a bit confused. They won't get the actual concept of it. So before starting this, I want to tell you a small thing that will take you deep into the concept of interference in Newton's ring in transmitted light ray. Actually, what is happening is, the thing is, on this lens, if suppose, for example, on this lens, if I am getting these many lights, so I'll represent it with some intensity represent. So I am sending lights with all having 10 intensity. So the pattern which I got here with the microscope is something like this. Just I need your focus here. So when I'm adding up, so whatever the pattern I'm getting here, when I'm adding up all the intensities of the bright fringes, what I'm getting is, I'm getting 5 intensity. So the question here is, I am falling light with 10 intensity, but the pattern which I got, the interference pattern, the Newton's ring, are having only half of the light is present on my reflected Newton's ring. So where is the 50% of intensity of light, intensity of incident light is gone. So that intensity, that remaining amount of light will produce the Newton's ring in transmitted light ray. That will form here. And this pattern will be exactly opposite of this. If at some particular thickness, if you're getting bright here, at that same particular thickness, you will get dark in here. The condition will be exactly opposite of it. So this is as a whole, if I say okay, all the light rays are hitting here, it's as a whole it's a 10, but some part of it is not having the light, so that part is covered by the Newton's ring in transmitted light ray. So here you're not having any light at this particular area, but that light is coming here. That's why here that part of light is absent. Why? Because that light has taken part into the interference in transmitted light ray. That's why here you are getting a bright spot. And at the same time, here the second dark is missing, some part of light is missing, and in here the reflected light ray, that light, where is that light is gone? Because you have sent it all of it, but some part of it is missing. So where is that light? That light has taken part in here. This is that light. So as a whole, when you add all the intensity from the transmitted light ray and all the intensity from the reflected light ray, that will give you the net whatever you have sended, the 10 amount of intensity. That is the conservation of light. Okay, so here's what you are gonna get in transmitted light Newton's ring in transmitted light ray. So by just observing experimentally the data, by, by just observing experimentally, you can say that the conditions of getting bright and dark spot in these both the conditions will be exactly opposite. Why? Because at this particular thickness, if you are getting a dark here, so this particular thickness is satisfying the dark. So that particular thickness is satisfying a bright here. So the conditions will be flipped. Now we'll try to understand what is the working, what is the phenomena which is undergoing in the thin film and which is causing to produce this beautiful circular fringe pattern, okay, due to the transmitted light ray. So let's try to understand that. So for that purpose, what I'll do, instead of taking angle of incidence 0, only just for the explanation purpose, what I'll do is I'll incident light with some angle, but that is not the reality. When I take the angle in the expression, I'll take it to be 0. That's how the value of R will get 0. Okay. So if I talk about the whole story, the whole suffering of the wave, this is how it is. So this is my incident light ray. So I won't be flipping any reflection or refraction or transmission. So this is the reflection from its top surface. Because it's a glass, part of the light ray will get transmit, and there is a boundary of air to glass. This is a plano-convex lens, but its medium is a glass medium. So because of the glass to air boundary, the light will suffer reflection and part of it will get transmit. Okay, so now again this light ray, this will come out. Now you see again there is a boundary. Where there is a boundary, light will suffer reflection and transmission. So part of it got reflected and traveled in the upward direction towards the lens curvature, but the part of this light ray will get transmit. Let this be my T1, transmitted light ray 1. Now because of this boundary, the boundary is from air to glass, again there is a reflection. So now this transmitted light ray is producing two lights. These two light rays are coming from a single source, and they are these two light rays are coherent and they are near to one another. They can produce the interference pattern. So the story is something like this. So they will produce the interference patterns. These light rays will produce this pattern and these light rays will produce this pattern. So the total light will be conserved. Half of the light will come in the reflected light rays and half of the light ray will come in transmitted light rays. So now we will be finding the path difference. Sorry, we won't be finding the path difference. Already we did in wedged shape film. So it is exactly similar to that. So this is also a wedge kind of thing, having some angle, but the angle here is approximate to be where the angle here is very small. That's why we'll take theta to be equal to 0. And so the path difference which we got in the wedge shaped film was 2 mu t. I'll take a sub n. Some particular thickness will produce some particular order of fringe into cos r plus theta, where theta is the angle between the wedge, angle between two glass slabs which are forming the wedge. And this is the angle of refraction, and we got this term due to the reflection due to denser medium. When light suffers reflection from denser medium, that's how this path difference will come into the path difference. But you see here, this light ray is getting reflection due to the denser medium 2 times. So because of getting reflection from the denser medium 2 times, this term will vanish. No need to take that term, because if first reflection will produce this path difference of lambda by 2, when the same thing happens again, that will cancel this lambda by 2. Okay, so as a whole we will be remaining with 2 mu t sub n cos r plus theta. Now we'll change, there are few more changes to do in this equation. What is that? The theta is approximately equal to the 0, and because the angle of incidence is equals to 0, that's how we can write r is also equal to 0 according to the law of reflection. So because of these things, we can write r plus theta is equals to 1. And we know that the medium which we got between the lens and the glass is a air medium. For that air medium, the refractive index is equals to 1. So it turns out that our equation of path difference will be 2 sub n. So this is my equation. Let this be equation number 1. So this is the path difference between these two transmitted light rays. So now I want to find out at what particular thickness I will get the constructive ring or the bright Newton ring, and at what particular thickness I will get a dark Newton's ring. So for that part, what we have to do, same thing. Take the general condition of getting a bright fringe. What is the general condition for getting bright fringe? Condition for bright fringe or ring, the path difference should be n lambda. So if this path difference is equals to this, you will get a bright ring. So it will be 2 t sub n is equals to n lambda. So t sub n is equals to n lambda by 2. So you see, can you notice something? You see, the same expression we got for the reflected light rays, but that is for the dark fringe, not for the bright. So this is how it will take care of these things. So whatever you got here as the condition for bright, that condition will be here for the dark. Are you getting my point? Now for the dark fringe or ring, the path difference should be equal to what? How much should be the path difference? It is 2n minus 1 lambda by 2. Let this be equation 3. So from 1, let this be 2. So from 1 and 2, if the path difference, if this path difference is coming out to be the odd multiple of lambda, then you are sure to get a dark ring. So let 2 sub n is equals to 2n minus 1 lambda by 2. So 2 sub n is equals to 2n minus 1 lambda by 4. So this is the thickness for, if you want to find out what is the thickness, at what particular thickness I am getting a first dark fringe, put n equal to 1, you will get to know. And if you want to find out at what particular thickness I am getting the first bright fringe, put n equals to 1. Now we will see what is the relation between the diameter of the rings with the order n. So for that purpose I have to find out the radius. So we have the equation for the thickness in terms of the radius, r sub n square by 2r. So let's find out first the diameter of the bright fringe, and we'll see what is the relation with n, how the diameter and n are related. So we have to put this equation, let this be Roman number 1 and this be equation 4. So if I substitute this thickness in here, here's what I'm doing. I'm finding the diameter relation, how d and n are related. Okay, so if I substitute the t in here, r sub n square is equals to, here I'm getting 2r lambda by 2, this will be n over there, 2 will get cancelled, and we know that r sub n will be equal to d by 2. So d sub n square will be equal to 4r n lambda. So d sub n is equals to 2 under root n r lambda. So how the diameter and order of the bright fringe are related is, the diameter of the bright fringe is proportional to under root of n. So this is how they are related. So this is for the bright ring. So you can notice here's the same expression. You see, this is incredible. The same expression we got for the dark ring in the reflected part. So here this relation is coming out for the bright ring, but the same expression, but the same equation was there, same relation was there for the dark ring in the reflected interference pattern. This, you see, these thickness conditions are flipped. Similarly, the diameter relations are also got flipped. Now, similarly, we have to find out the relation of dark ring diameter with n. So here's, let this be my equation 5. Now we have to substitute the Roman number 1 in equation 5 to find out the diameter relation of dark ring with n. So it will be r sub n square, this 2r, if I take it to that side, that 2 with this 4 will get cancelled out, and it will be r 2n minus 1 lambda by 2, because the other 2 got cancelled with this 2. So the diameter, if I use this relation, it will be d sub n square is equals to the 4 4r 2n minus 1 lambda by 2. So this 2 will get cancelled out. And the final expression is something like this. It will be under root 2r 2 times of 2n minus 1 r lambda. So the relation is like this, under root of 2n minus 1. So the same relation we got, this relation of the diameter with order of fringe, we got this relation for the bright fringe in the reflected interference pattern. But here in the transmission light ray, we got this relation for the dark ring or the dark fringe. This was all about Newton's ring in transmitted light ray. So in the next class, we will be talking about some beautiful applications of Newton's ring experiment. We can find out the wavelength of a monochromatic light source with the help of this expression, with the help of this experiment. And we can find out what is the refractive index of the medium is. So thank you so much for watching.